Here we're going to pour some sodium hydroxide into nitric acid. When we do, it's going to increase in temperature quite a bit. And then the other one here we have some vinegar. We're going to add a little bit of baking soda. You can see the CO2 gas coming out there. When we do that, we see the temperature actually start to go down, although not as much as the other. So what we want to be able to do then is we want to be able to go through and analyze what's going on with the energy, both chemical and thermal, for these two reactions. So we just saw two reactions take place, one between vinegar and baking soda, the other between nitric acid and sodium hydroxide. In the one, the temperature of the solution, which is mostly the water surrounding the chemical mixture, the temperature dropped. And so we saw a thermal energy change of the surroundings and a decrease. And in the other, we saw the thermal energy of the surroundings go up. So we would traditionally call this endothermic and exothermic. We want to go through and break down what exactly is happening energetically from the start to the completion of that reaction. So what we're going to do is we're going to start with 2 bars of thermal energy. We're going to say we're starting at room temperature for our, and our system is going to be this chemical mixture. So we're going to put kind of our chemicals that are reacting. So whether it's the bicarbonate, the ethanoic acid, or the sodium acetate, or the carbon dioxide and water, all of the chemicals involved in this reaction we're putting as our system into the odor. From there, let's start with any amount of chemical energy, it doesn't really matter, but let's start with 2 so we have ability to go up or down as we see fit. So what's going to happen in this particular case is when we mixed them, we didn't have to heat them. So the chemical reaction just started happening on its own. And what we saw is we saw a change in thermal energy of the chemical mixture and its immediate surroundings. So what we're seeing happening is that thermal energy is becoming chemical energy for that chemical system. And so we're seeing that it ends up being at a lower temperature. And we're going to split this up into 2 sections here. At first, we're seeing the thermal energy of the chemicals go down, and that's leading to a rearrangement in the chemicals. So as these are changing to those, we're seeing the chemical energy change. So here we're starting with the sodium bicarbonate and the acetic acid. Here we're looking at the products of that, the sodium acetate, the CO2, and the water. Okay, so we call it our chemical mixture or chemical reagents. Then what's then going to happen is now that this is at a lower temperature than the surroundings, so those chemicals have slowed down, now they're going to be colliding with things at a slower rate, and they're going to draw energy from them, so we're going to see heat come from the surroundings. And so what's going to happen then is over time, eventually this is going to heat back up to room temperature, which means that when we feel it, we feel cold because we're inputting energy into the chemical system. And so we're losing energy from the surroundings, and therefore we measure that water that's surrounding these chemicals to be colder than what it was before. So we've increased the amount of chemical energy by drawing energy from the surroundings to replace that thermal energy. Okay? So the way we would describe that in terms of the chemical reaction is we would put some kind of energy term here at the beginning. So you see I put kilojoules. I don't know how many kilojoules. I don't know the correlation between the amount of energy in this particular reaction. But I know that some energy went into changing the chemical arrangement of those particles. Now in the other reaction, let's start again with room temperature and chemical energy. Again, it's not important how much chemical energy you have, you just need the flexibility to be able to move this. We could have easily taken 2 bars of this and put 2 bars here, whatever, it doesn't really matter. What's important is how these things are changing. So in this one, when we mix the chemicals, we saw an increase in temperature. So that's indicating that we are increasing our thermal energy. So in this case, we're going to be taking chemical energy from our chemical mixture, which is this chemical mixture. Let's actually put the chemicals in for this one. So we have our nitric acid and our sodium hydroxide. And then these start to rearrange to form our sodium nitrate and our water. And so as these are rearranging, they're starting to move faster. So the thermal energy is going up. So our sodium nitrate and water molecules are moving faster than these were. It's what we're seeing from our visual evidence, which indicates that our chemical energy has decreased to be able to account for that. Now then what's going to happen is, now we have a warm set of chemicals surrounded by water, And so that water is going to start to heat up, and so this is then going to release energy to its surroundings in order to eventually cool back down to room temperature, or we'll still be left with lower energy. So this is exothermic. Energy is leaving the system. Now it's coming from the chemical, but it's going through a process where the chemicals are doing a rearrangement, and those chemicals that have rearranged are now faster than the ones that they started as. So these are moving at a higher rate, or with more kinetic energy on average, than these ones were. Then those start to bump into the molecules in the surrounding, whether it's the water, or the beaker in the glass, or your hand holding it. And therefore you feel energy, or the surroundings feels energy coming out of that. But it's only from the thermal where that starts to happen. Okay. Now, this is one way to kind of organize what's going on in this reaction, and what we can see happening is that we are changing between thermal and chemical in the endothermic, and then our thermal energy is drawing heat from the surroundings, and that's where we see the endothermic process taking place. And then in here we're seeing the chemical energy converted into thermal, and then after that our thermal energy will transfer heat to the surroundings, and therefore we drop back down and we've ended up losing chemical energy. So the net effect in the chemical energy in each case. In this one, we start with a certain amount of chemical energy, and then it goes up. So if we were to draw a little graph here, and say, okay, here's our energy, and here's our reaction. We start with a certain amount of energy, and then it ends up higher than what it was before. Okay? Whereas in this one, we start with a certain amount of energy, and it ends up lower than what it was before. Now in theory, it could just go right up, and this could just go right down, meaning that in some reactions, the molecules that are produced are slower, or lesser in kinetic energy on average, than the ones that we started with. Or additionally, in this one, we could look at it and say, these molecules are now faster than the ones we started with. But what's more likely than that is that in each reaction, we see an increase in speed and a decrease in speed. So as these chemicals are reacting, something is happening internally based on their repositioning that's causing them to speed up and to slow down. And what's happening is at first, their potential energy is going up, meaning that they are slowing down. And then later, they're going to have the potential energy go down, which means they're speeding up. And so in this case, the molecules slow down more than they speed up. Now they're moving slower at the end, and so when I feel that, I feel cold, because I'm feeling molecules that are moving slower. In this one, on the other hand, the molecules slow down, and then they speed up a lot. And so now the molecules are moving faster than they were before, so if I'm the surroundings, they're going to bump into me, and I'm going to feel that as heat transfer to myself. So we see the energy going to the surroundings here, whereas in here, because the molecules are moving slower, the energy is being transferred into the chemical mixture from the surroundings. So that's a breakdown of what's going on energetically in a chemical reaction, without really getting into any technical details, but just based on observations that you can see in different chemical reactions.